Okay, so thank you all for your presence. First of all, let me thank the organizer of this wonderful forum, this seminar series on string phenomenology, to put all the efforts and inviting great speakers. So I'm going to talk about some insights about global model building in the context of string theory, with some emphasis on choosing the Calabi-Yaus and things like that. So in the type 2b context, the modular stabilization is actually classified, can be classified in five categories. One which uses non-perturbative effect, and others which don't use non-perturbative effect, as we are very choosy. So we used to have many possible alternatives of this. So namely, we have KKLT, LVS, racetrack, perturbative LVS, and tree level. And there's a huge amount of literature which is available in this class of models. So I apologize for not including all those. It's not possible to do it here. So thanks to my diverse set of collaborators, that I have a little bit to contribute along all these five possible modular stabilization direction. But the aim of the talk is to actually present something else, which is actually taking a phenomenologist approach for global model building. So I will take these two modular stabilization scheme, namely the one with European way in the lighter note again, and other one is the American way, the KKLT. So by the statistics of the available literature, I think it could be said so in some sense. So I'm going to talk about some LVS inflationary model and try to see what are the problems with those models, and how one could actually vaccinate those models, in the sense that they are more and more robust for future possible corrections which appear in the way of doing that. So I'm going to talk about this KKLT a bit, about the flat vacua analysis in the sense of divisor topology implications and some generality with the KKLT. So with this talk, the first one is the paper yet to appear with Michele, Matteo, and Pellegrino in Bologna, and Fernando in Damt. So in the KKLT part, these three papers are actually in collaboration with Federico and Alessandro. So I'm going to take this very light discussion, in the sense of having some starters. So why global model building at all? So we have just too many attractive models, we can say, and unfortunately there are no filter yet which is available to us to rule out some model. So we have on the course of time, we have created our own special task force from time to time to deal with this kind of a thing, and create our own check and balance, in the sense of swampland conjecture or weak gravity conjecture was in the market for 3-4 years or so. Then we have the swampland. So on the global model building attempts, so I would say that this is a theoretical lab, in the sense that one can support or challenge the models in their present minimalistic form. We used to propose model in the simple way, and then assume many things and expect many things. The question is how correct those presumptions or expectations are there, and what is the reality. So in this sense, I'm going to talk about the questions like which Calabi-Yau is the suitable one. So there is always this take any versus give me the right one kind of thing. So we have like 500 million reflexive polytopes, which results in a huge number of Calabi-Yau, and then there are various possible avenues which are available for dealing with this Calabi-Yau, like some Fano data set available from Ross Altman and Gray and he and Zala and Nelson, and then this is a projective complete intersection Calabi-Yau, generalized complete intersection Calabi-Yau. So the point which I'm trying to make is that there is a huge number of data set which is available, and which is also accessible in the sense of doing phenomenology. Earlier it was not so, but now we have very interesting toolkits like Pulp, Sage, Singular, Calabi-Yau tools, and Cohom, etc., which actually facilitates the kind of approach which we can perform in doing those kind of computation, and checking whether those models of simple nature which are attractive are really simplistic, are really realistic or not. So with this one in mind, I would try to kind of relate this by taking a phenomenologist view, in the sense that these Hodge numbers are related by the counting of moduli. The third Chern class is the BBHL, this Baker-Hartley correction of alpha prime. Then second Chern class is actually higher derivative up to the 4 correction, and then this there's no first Chern class. That is lucky for us, and also the very same reason why we use Calabi-Yau. So there's no correction induced out of C1, and then we have this triple intersection number, which gives me the facts about Swiss cheese, K3 fiber, and other things. So then we have these divisors inside the Calabi-Yau, these 4 cycles, and they have very interesting phenomenological implication in the sense of how the brain setting is made and what type of corrections are actually generated in this situation. Like rigid divisors are needed for having this non-perturbative superpotential contribution, LVS, and blow-up inflation. So I'm going to talk about all these in some detail, but I'm just giving a reflection that there is like a one-to-one correspondence, which a phenomenologist kind of approach can just consider them to be. And then we have K3 fibered Calabi-Yau for fiber inflation, Wilson divisor, or some specific type of divisor needed for polyinstanton effects. And then we have some special deformation divisor, and the Taylor cone condition is of course there, which actually restricts the field space for the flat direction, even if it is even if it is flat, you cannot move arbitrarily in the field space. There are Taylor cone condition which restricts you to do that, and things like that. So with that in mind, I would there's no need for a kind of motivating LVS for this audience, but just for the sake of completion, I would just put a few slides in the sense saying that LVS is very robust and very trustworthy model. It has passed several tests from time to time, because the time evolution of corrections which we know in string theory, they are very uncertain. Sometimes they are supportive, sometimes they are not. So luckily this LVS process actually utilizes these subleading corrections like alpha prime and the WNP, this non-perturbative correction in W. So it is like a useful control of the overall framework, in the sense that it actually generates the volume into very large value. And then the models built within LVS are quite robust as well. So the question is, what is the type of viability which LVS actually enjoys? So it has passed several tests like extensions in the noise scale structure. In the sense of GS, this string loop correction to scalar potential appears at a higher level as compared to alpha prime. But when you compute the scalar potential, then there is some precise cancellations, which are actually known as extensions of noise scale. So the idea is that within LVS framework, one can actually engineer various type of corrections with some kind of a hierarchy in the volume powers, and then build model in like a step-by-step mechanism. Like for inflation, you have to fix like all the other moduli field to heavy, and then use one field or two field for your inflationary purpose. This is just the simplest model building kind of approach which one follows. And then in this LVS framework, there are 3 classes of models, named as Taylor moduli inflation or blow-up inflation, fiber inflation, and polyinstanton inflation. They are very attractive and have their own features. So all of them are 3-field models. That means 3 Taylor field, and 2 of them are fixed by LVS, and the remaining one work as the inflaton direction. So then we have this in the blow-up inflation, we have this volume given by like a strong Swiss cheese, and in the fiber case, it's like a weak Swiss cheese. And then for the polyinstanton case, there is some other kind of special divisor known as Wilson divisors. And these 2 corrections are first one and third one are generated by the non-perturbative effect. In this one, fiber inflation, in the inflations, the source of inflationary potential is actually a string loop correction. So we have actually tried for global embedding of all these 3 models. So as in that sense, one could say that these models are vaccinated by the first dose. So in the sense that we do have some global embedding model proposed at the minimalistic level. But the question is, from time to time we face new challenges, and one has to deal with them and then make them keep working for a longer period of time with the viability assured. So for just as a snapshot of fiber inflation, we have this volume given like a weak Swiss cheese example. So this one corresponds to the del Pezzo, contributed negatively, and then we have a K3 fiber Calabi-Yau contributes like this way in the volume with the K3 fiber here, and then non-perturbative effects to fix the volume in terms of LVS volume and tau s. Then the one direction which is left flat is actually fixed by the string loop effects, which are very specific to the local ingredients in the sense of brain settings and so on and so forth. We will come to it, but the idea is you have a potential with 3 terms. The first 2 terms actually determine the minimum, and the third one determines this steepening, and in between you can engineer these A1, A2, A3 to have a plateau. And this has some very interesting cosmological implications. So it's a very interesting model, and the global embedding part we have actually performed in a very simplistic way by taking a 3-field H11 equal to 3 Calabi-Yau, to have these 3 Kähler moduli. So the idea is this for global model building. So you have to choose from some suitable Calabi-Yau for your minimalistic model which you have built up, and then find whether those kind of Calabi-Yau has appropriate divisors and to ensure those corrections, and then involution, tadpole cancellation, blend setting, and also one has to make sure that there are enough corrections and those corrections are appropriate as well. Sometimes you do have enough corrections but they are more than enough, and some terms are killing your scalar potential itself. So it should be delicately engineered. So message is this, and then one has to also incorporate the new terms which arise in years to come, like high derivative correction came later on, and one has to investigate this. And then of course modular stabilization, inflation, chirality, and Kähler cone condition can be implemented to see how things are working with inflaton direction. So with this in mind, I would just put this heavy slide. I'm sorry for that, but the only message is that this is one slide summary for fiber inflation in the context of global embedding. So one has a Calabi-Yau. So the idea is to start with you have 305 Calabi-Yau geometries. Then some 568 triangulations are there arising from 244 polytopes from the Koster-Skarke Calabi-Yau database. And when you impose the condition of being K3 and K3 fibered and also having a diagonal del Pezzo divisor to have the LBS, then there are only 43 which are left out of 305. And then out of these 43, if you start choosing the involution and making the blend settings to work, some kind of appropriate correction which should survive, and some type of correction which should not survive, in the sense that this correction could be dangerous, but because of a P1 sitting here, it would not contribute to the winding mode because P1 is a shrinkable 2 cycles. So the idea is that for winding correction, you need to have intersecting brain which don't intersect on which intersect on a non-contractible cycle. And for KK type correction, you need to have parallel brain settings such that there is some transverse distance between them to contribute to the Kähler potential. So in the end, you generate this kind of a 3-term scalar potential, which is exactly the case of fiber inflation. But for critique, one could say that after doing all these tedious work, in the end we find this model which was the better among the better ones, not the best one, which has like tadpole with just 9. So you don't have much freedom to tune the F3 S3 fluxes, and there are so many other things which appear on the way. So in this case, then we have another restriction coming from the Kähler cone condition, and this work was even before the swampland revival happened actually in 2018. So we observed that this after imposing the Kähler cone condition, the plateau which is actually appearing in the fiber inflation case is actually obstructed by the Kähler cone condition itself. You see this vertical middle line, that is a restriction of the Kähler cone wall kind of. So you cannot generate 60 number of efolding unless you increase your volume, because there is a kind of bound with the field range to the log of the overall volume of the Calabi-Yau. This overall volume of the Calabi-Yau is actually adjusted to match with the cosmological observable, like the scalar perturbation amplitude. So you cannot play much with this apart from having this flux super potential term. So the main message is that you don't have that clean thing to make it work as we do in the 3-field case. So this Kähler cone condition is right on the top of this plateau. So there is something you have to worry about, and mend your model in such a way that it again restores the interesting thing and keeps working. So with this message in mind, I would just come to the next one to make the higher derivative contribution and check with how dangerous or how interesting those could be. So they are actually these F to the 4 correction. They are not the 2 derivative. They are beyond this 2 derivative scalar potential and super potential approximation, but they directly contribute to the scalar potential. And there's one topological quantity tau, this pi alpha. And pi alpha is a divisor which will come to which will come to. So the idea is how to make this pi alpha vanishing by finding some appropriate Calabi-Yau examples. And this is very interesting case that we are closely monitoring this since January 18. We have the data for all the Calabi-Yau which have this vanishing pi and something which don't have, but it's very challenging to fit everything together, I would say, in some sense. So the idea is to have some classification of divisor before coming to it. So a divisor has four independent Hodge numbers, in the sense that there are other relation which actually make it dependent, like Poincare duality, and the 2 of them can be determined by this d cubic and the C2 expression. So one can compute the second Chern class and the cubic intersection number on the Calabi-Yau. So one knows how chi h, the arithmetic genus, this minus this plus this, and the Euler characteristic of the divisor works. So for example, for del Pezzo case, we have this pi of dpn for a del Pezzo of this order n, where n is actually the number of blow-ups. So n equal to 0 means a p2, and then you increase the number of points in a p2 to get the del Pezzo. So for K3, you see it's a 24 because for cubic intersection vanishes for K3. For T4, everything vanishes. This chi h vanishes. Arithmetic genus is 0. Euler is 0, and D cube is 0, and so pi is 0. But T4 is just a very simple toroidal friend. And for this so-called Wilson divisor, we have this condition on the H11, which actually makes it to so by the way, this work is actually still in progress. So we hope to put it in near future. And then if we see these kind of relations and then try to classify, then we find that for because the blow up inflation uses the del Pezzo divisor, so we would need a very naive guess says that we would need dp3 divisor to have the blow up inflation, and T4 for the fiber inflation, and then for Wilson divisor we need H11 equal to 2, and this is precisely what was actually done in this previous paper of mine with collaboration with the Ralph Blumenhagen, Xing Hao, and Thorsten Rahn. So we actually proposed the global embedding of polyinstanton inflation, and at that time we did use the H11 equal to 2, the Wilson divisor were such. So the idea is actually we have a full scan of all the vanishing pi topology for the divisor with H11 equal to 5 for the process Karke database, and we can find that within LVS you can have like n LVS means one del Pezzo which is diagonal, and then you can have number of a number of one divisor with vanishing pi, 2 divisor with vanishing pi, and 3 divisor with vanishing pi. They're just unique one with H11 equal to 5, and so on. So we have the full classification of this, and it's a very interesting one, but it's still challenging. So like the other property of a divisor is a del Pezzo, and the diagonality of del Pezzo is described by this condition on the triple intersection number, and we find that actually very interesting actually. It's a purely empirical observation, but del Pezzo of the degree which are like defined by say 1 to 5 for n, degree of del Pezzo is actually given by 9 minus n. So for n equal to 1 to 5, the dpn actually is non-diagonal, which appear as a divisor of the del Pezzo of the Crosser's database. So we have realized this after studying a huge number of Calabi example, and this is like some empirical observation which we conjecture that maybe it is true for higher H11 as well, and one has to really check it. So, and then here's a kind of some estimate about the LVS inflation. So first one is for blow up, second one in the middle is for K3 fiber, and third one is for the polyinstanton case. So it is in the interest of looking for the f to the 4 corrections. So in that sense we wanted to see how things were before including the f to the 4. So this is like a standard blow up inflation, standard K3 fiber, and standard polyinstanton. So for H11 equal to 3, this is the 43 number you see I talked about. So out of 305, if you impose the K3 and diagonal del Pezzo condition, you get only 43 example, and the one example out of this 43 was like more or less working in some sense, having some limitation. So this is the kind of statistics which we have for all the process Skarke example up to H11 equal to 5. So far so nice. So then we can actually kind of extend this program of studying the divisor topology for the coordinate divisor. What we are studying is actually coordinate divisor, which are part of the GLSM charges. So in that sense, the Cohom calc is a very efficient package which helps a lot. So for the smaller H11 it is very fast as well, but for a larger H11 it actually becomes very slow and sometimes breaks also for some examples. So the question is there a way to kind of bypass the need of Cohom calc? And so it's not a very rigorous way of doing what in a mathematical sense people would like to do, but there is some kind of observation which one could definitely make, and is that if you take the favorable Calabi-Yau, then all your Calabi-Yau are all your Calabi-Yau divisors are actually descending from the ambient space. That means if they are smooth, then H00 would be 1, and if they are simply connected as well, then your H10 would be 0. So, and then there is another possibility. So the observation which we make after computing the divisor topology of all the Calabi-Yau up to H11 equal to 4 and half of the H11 equal to 5 is the fact that either you have H10 equal to 0 or H20 equal to 0. You cannot have both of them to be non-zero. And based on that, we can actually make 2 classifications. So now we have fixed 2 of our Hodge number out of 4. So the remaining 2 can be determined by chi h and chi, which are determined by the triple intersection number and C2, which we just discussed. So the idea is the same idea we implemented for the projective CCs as well. And in that case, we find that there is just one possibility, not the 2. So this chi H10 is always 0. So in PCCs, all the coordinate divisors are always simply connected. So this number is always 0, and then this number is 1 if you take the favorable case. and then the two of them can be determined by, so by the way, I just call this H00, this is H10, this is H20, and this is H11. These are the four divisor which actually, four Hodge numbers which classify my divisor. So interestingly, or bad for on our part, that we don't find any T4 divisor appearing as a coordinate divisor of the favorable process car K, as well as all the this PCCs which we studied. So it's a very, it's still observation, but a good conjecture to make. And for the CC case, we actually were surprised to find that there are like 7820 number of Calabi-Yau spaces with more than 57,000 divisors, and there are only 11 distinct kind of divisor topology, and most of them are covered by K3, or what we call a special deformation, and here we are calling it T2. So this is actually H00, H10, H20, and H11. So this is actually the divisor which very often appears in process car K as well. For example, if you recall this 11169 example, those 111 actually are these topology T2. So it's very interesting that they both of them have cubics also vanishing, K3 as well as this special deformation, and they cover most of the examples. So most of the divisors are only of these two kind in the PCCs. So it's a very interesting observation to me. So then let me just come to say a bit about KKLT part also, in the sense of, so we have very fascinating proposal of this this cornell group that low W naught can be analytically realized. So having low W naught is actually was supposed to be a matter of tuning. So this paper actually kind of challenged that usual notion of what is tuned and what is not tuned. So in a very natural way, they managed to realize exponentially small W naught, and we actually build up on that proposal to implement that for all the Calabi-Yau which are H11 equal to 2 for clusters car K as well as CCs. And we find that there are some interesting patterns. So this slide is only for those who think that maybe global embedding is just a useless thing to do, because if it works for one example, what is the need for finding it for another example? It has its implication, because by doing this analysis for working out for all the examples in the clusters car K with H11 equal to 2 and CCs, we find that K3 fiber Calabi-Yau turned out to be the special one. So they have more number of these perturbatively flat flux vacua, what we call PFFVs, and we find that Swiss type example have either no flat vacua in the end to be physical, or just a unique one up to n flux being 150 or so. So it's a very interesting observation. And then there's also observation that number of Swiss cheese Calabi-Yau decreases, but not the number, but the percent of Swiss cheese Calabi-Yau decreases, while the percent of K3 fiber increases when we increase the H11. So the question is, more or more Calabi-Yau with higher H11 or K3 fiber. So far we have been kind of ruling them out in our no interest, and this actually put them back into the game, a la KKLT. So if you have W naught smaller, then you can do KKLT, for example, and do the rigidification of divisor. But this is just H11 equal to 2 observation. So what happens for the case of H11 equal to 3, which can have a K3 fiber, which is Swiss cheese also? For that, you need to be a bit stay tuned. So we are still like on the way of finishing it. 80% job is done, I would say, but still, I mean, so okay. So with this one, I would say that this is just some flag analysis for the clusters car K with H11 equal to 2, and this is before fixing the dilaton value. So in this case, the dilaton value is fixed by the non-perturbative effect. So it is before fixing that. Otherwise, this number also reduces quite strongly for those which are not K3 fiber, and you can only see peaks for the K3 fiber. So that's fascinating to see. So in this one, then I would just conclude by saying that. So I just motivated the need for having a global model building in a phenomenologist friendly approach, and presented some kind of classification of divisor topology for clusters car K as well as these PCCs. And there are some kind of observations based on what topology could appear and what not. And for the high derivative correction, we are actually giving it full try to try to manage all the things work nice and fit so well. But from the kind of finding the Calabi-Yau with the appropriate topology with the smaller H11 say up to H11 equal to 4 5, it seems to be challenging or delicate, but of course nothing is ruled out by it. So hold your horses in that sense if you are trying to conclude to something immediately. And then there's a role of this perturbative flat flux vacuum for this divisor topology, for which K3 fiber are singled out. And I didn't have the time to discuss for this exponential flat vacuum, but that's also part of the symmetry of the if the Calabi-Yau has some symmetry, then it turns out that the flat vacuum actually may have a subclass in the sense that it is not only protected at the leading order, but also with the non-perturbative effect. There is a perfect protection. You cannot fix them. So you cannot fix the dilaton value, but that doesn't mean that the whole prescription is a useless thing, because you remember that you are still fixing the complex structure along the dilaton. So that alignment is already done. So only the dilaton cannot be fixed by this exponentially flat backward. So then here is some concluding remark in that sense. I would just say thank you for your kind attention, and I really apologize for all the problems with the internet connections, which really was bad on strange situations. So, and just to say one more thing about thing, that if you are interested, and I'm giving the opportunity, then we have some kind of master formula for reformulating the scalar potential, but that's a different story, and I would like to tell this story in a different talk, and hopefully that time the internet would work and we can have it live on. So thank you very much for your kind attention, and thanks a lot. Thank you so much.